space group that has this additional translation symmetry built in. Okay, and this is a huge amount. This is a table of all 230 of them. Again, don't just to impress you that you could do this. You could write this all out, and if you take a diffraction course, X-ray diffraction course, you can ask your instructor to explain this. And these are the different notation. Again, the Herman notation here, and the other, the standard chemistry notation on the other side. So when you see, for example, if you read literature, I point this out, and I include this table just so that in future, if you come across some literature and they listed, for example, FMMM. What is FMMM, right? So you can go cut back to this table and look up. You know, FMMM is really have the D symmetry, D2X symmetry, right? It's a certain type of D2X symmetry, and then you can sort of maybe figure out what they are, right? So this is just a translation table for future reference about the space group that you see. And sometimes when you read literature, you may see this because other people, if you have a complex ceramic structure, oxide structure, people often list this sort of notation, and now you know what they are. And now you can sort of figure out, at least get a start to figure out the respective symmetry that we are familiar with in this other notation. Okay? So, not a big deal, it's just a classification and so forth. Now, next I want to tell you a little bit about plane, right? Because we are starting, we're breaking down, so we cover so far a very crash course on this, you know, bow structure that often talk about in solid state chemistry or physics. We talk about plane because eventually we need to connect it to a surface, and a surface is a plane. It's maybe 2 or 3 planes on the top of your bulk material. Okay, so a plane, how do you define a plane? So a plane is really just 3 points, any 3 points, and they're not 3 points, not in a straight line. Okay, 3 non-collinear points. Collinear means they lie in the same direction. So if you have 1, 2, 3, like all in the straight line, that's a collinear point. So you have 1, 2, that is collinear with respect to each other, and then you have 3, like this. Then all 3 points are not collinear, right? This is all 3 points are collinear because they all lie in a straight line. In a straight line, of course, you cannot define a plane. If you have non-collinear point like this, then this, of course, what I just drawn will define a plane. Okay, so that's how you think about it. So you can virtually define in general, and give me 3 points, they are not in a straight line, then you got a plane. But it's easier to use this thing invented by Miller, called Miller indexes, that we all heard about in chemistry or physics courses. So Miller indexes often is given notation H, K, and L, and so you write the plane notation in round bracket, and the normal of the plane is written in square brackets. Okay, so that's something that I want to point out. Sometimes when you read again literature, you can tell what the individual is talking about. If you use square notation, that means it's a vector. It's a vector normal to that plane. He's not talking about the plane itself. Okay. So here, for example, this is round bracket is 110 plane, and these are family of 110 plane. And so first of all, just remind you how to get these Miller indexes. And there's a simple recipe to do this. The recipe is very simple. So find there are 3 steps. So find the intercept of this plane on this A, B, and C axis. So let's say A is X direction, B is Y direction, and C is in the C direction. A, B, and C is often used as the unit vector of the lattice axis. So it's like a unit vector of lattice vector in x direction, y, and z direction. So the first step, find the intercept of the plane on this axis, A, B, and C axis, in terms of lattice constant of the unit cell. So in unit of, for example, this book is not so good. So usually they assume when they do this sort of thing, they assume cubic unit cell. So when they assume cubic unit cell, all three axes have the same dimension, but they don't have to be. Usually you call this one A axis, unit vector axis, and this is B axis, and this is C like this. Okay? So really, that should be B here, 1B, 2B, and 3B, and this should be A on this direction. Okay? So you take the intercept. Let's say you look at this plane here, this one we have. So it intercept at 3B, right? Let's say 3B, and it intercept at 3A, right? And the other one, it does not intercept the z direction, so that's infinity, right? And then what you do is that, so the other one is infinity c, right? Kind of things like that. So, okay, then the step 2 is just take the reciprocal of this number, divide by the respective lattice, divided by the lattice vector constant. So divide by A, B, and C respectively. And then you generate this xk and L fraction. And then you scale it up to become a nice number. Okay, so let me give you an example. It will be confusing to talk like this. So now let's look at this one, for example. It's really quite simple. So if you look at this one, I have intercept. Let's say I have the first step. I have find the intercept. This is intercept. This plane, highlight the plane. Intercept at 3A. Right. So this is one point here. This is 3A direction. And intercept at 3B, I will call this B now instead of A because it's in the y direction, 3B. And this one intercept at 3½ C, right? So this book call everything A. I call this one A, and this one B, and this one C. That's the unit vector in 3 different directions. So that's the intercept that I found. And then I take the inverse of that and divide it by the respective lattice vector constant. So I divide this by A. So you can think of it, take A divided by this, B divided by this, C divided by this. And that's what you got. You got 1/3, 1/3, 2/3. And then you find a constant, because it's difficult to write fractional number. So you just multiply a common constant to make it into nice integer. So you multiply by 3, you get 112. So this is a 112 thing. Okay. So rather simple. So that's the free step in generating these this thing. So if you look at this one, for example, what is this one? Well, this one is just we can do this one. So this one is it intercept at infinity A, right? Because it doesn't intercept x really. But it intercept, if I'm looking at this plane here, it intercept at 3B, right, like this. And then it intercept at infinity C, right? And then now I take A divided by infinity A, right, and B divided by infinity 3B, and C divided by infinity C, like that. Okay? And of course, this is equal to 1 divided by infinity is 0. This is 1/3. This is 0, like this, right? And then I multiply everything by 3, right? And so I multiply by 3, and then this is 0, this is